Thank you, Finton, and welcome everybody to the first proper day of Thingmonk. No, yesterday was the first proper day. Yesterday was brilliant, wasn't it? It was pretty cool. So this opening talk, the keynote, was supposed to be given by Chris O'Connor, who's the general manager of Internet of Things offerings for IBM. But he pulled out at the last minute, so it got dumped on me. I reviewed the code of conduct this morning, and some of my opening comments about Chris I now can't make. Oh, right. Anyway, the good thing about doing a general manager's presentation is you get excellent slides, and we have some excellent slides. So even if you don't particularly like the content of this talk, and you may or may not, the animations are fantastic. I may stop from time to time to let the slides speak for themselves, because they are really quite excellent. Stereo, no more. Okay, so if you don't listen to anything else in this talk, listen to this little bit, because this tells you what a digital twin is. The rest of it is kind of examples and meat on the bone and sort of explaining it in more detail. So the idea of a digital twin is that you have a physical asset of some sort, maybe a plane, or it could be anything. It could be the power consumption in your house, it could be a patient in a hospital, all sorts of things. And you build in your computer a digital representation of that physical asset, a model of it. And you take real-world data from the physical asset, and you feed it into the digital model so that the two stay in sync. And then instead of having to do interesting experiments on the physical asset, like, what happens if we double the load on it, or what happens if we only put in half as much oil, which could be a bit detrimental to the asset itself, you can do those kind of what-if experiments on the digital twin, the model, to see what happens. And that is really the power of this. So you're feeding the model with real-world data, and you tune the model to make sure they stay in sync. And then you can play interesting games with running time forward, looking at potential different scenarios. You can fork the digital model and look at other possible scenario paths. You can do analytics on that data in order to find out what would happen if you treated your physical asset in a different way. Okay? That, in summary, is what a digital twin is all about. Now enjoy the graphics. So a digital twin brings benefits in all stages of a physical asset's life cycle. First of all, in the design phase, if you're getting feedback from the ones that are already out there, the ones you've already made, then you sort of close the loop on that feedback cycle and enable the operational insights to give you better design for V2, V3, and so on. So rather than having to sort of take arbitrary observations, you've got the benefit of the full data of the digital twin, the model of it, to pick at and say, what if we change this aspect of it? If you're building things in manufacturing, the fact that you're getting data back from not only one of your assets, but a whole ensemble of them, all feeding back things, means you start to see systemic problems in them. So rather than just the occasional item that got returned because it was faulty, you start to see systemic problems emerging across the whole range of your physical assets, which you can then very quickly feed back into the manufacturing process to nip any manufacturing defects, or indeed to make changes to the manufacturing process in order to improve things. So it's a continuous improvement process. And then when you're operating the asset, fairly obviously, because this is the kind of stuff we do with IoT all the time, then because you're getting real-world data from the physical object feeding the digital twin, then you can start to do predictive analytics. You can start to look at what happens if we change these maintenance schedules. And so basically you get informed service and support for the physical assets through the value of the data that's coming, the analytics you're doing on the digital twin. Wait. Fantastic. They must pay someone to actually make these. I assume they do. I mean, I have to make my own presentation, but I'm sure Chris doesn't make his own ones. So analytics at every step. So the key point here is that once you've built your digital model, in a sense, it's just going to sit there unless you do something with it. And the value of it is if you start to play what-if games and start to ask it questions. So by doing analytics at a number of stages in the process, so first of all, doing analytics at the edge to filter down that vast amount of data that we're getting before sending it up to the IoT platform, and then we might do some processing there before feeding it in a sort of a filtered way into the digital twin. Quite often you don't ingest all the raw data into the digital twin. You quite often feed it samples of a representation of what's happening. But you can do, but it just depends on different things. So different processing at different steps, and that we may return to that theme later. It might be Martin and Chris, Charlie. Yeah. So the idea of then getting the insights from that model that you could have got by physical measurement, quite often you couldn't have got by physical measurement as well. So you can have derived variables that you could only get from the digital twin that you couldn't possibly have measured from real-world quantities, so synthetic values made from the combination of different sensor values. Open and federated data. So very important to the digital twin is often bringing in other data from outside the ecosystem, often bringing together multiple data sources into one place, and often other sources of data as well, so things like weather data or historical data, or maybe manufacturers' spec sheets, or the original sheets that came with a particular asset. So if you've got a complicated system that's a system of systems made up from components, the fact you can then see back into the history of where they all came from means you're pulling on different data sources from the digital twin that might give you some insight into maybe a particular supplier somewhere way up the supply chain just happened to have made all the cogs which later cause a defect in a gearbox, and you can trace that back. An industry context is very, very important. If you just build a digital model from some sensor data, chances are it won't tell you the kind of things you want to know. As somebody very much wiser than me said, data plus context equals information. If you haven't got that context, then you don't get the information, you just get left with the data. And we always sit down when we're building a digital twin with a subject matter expert from the particular industry or the particular client we're working with to say, okay, what happens when this happens, or what does that number mean? And they tell us, and you can build that real-world industry knowledge into the model itself, so it becomes clever. It appears smarter right from day one. Wow, look at that, fantastic. Okay, so we have our digital twin with all the ones and zeros going around the outside of it, and the key thing is that from the outside, we're feeding in sensor data from a variety of places, from all the different assets, from different sensors on the data, and that's coming in through in our case, into what's an IoT platform, and feeding into the digital twin. When we've got the data in there, it's feeding the model, so it's alive and sort of making a parallel or twin of, hence the name, of the physical asset. Then we can start to apply the analytics and get what we term cognitive insights, or the actionable insights. In other words, this is what you should know and should act on based on what we're seeing in here. So there's no point in the model just being a parallel of the physical system. You actually want it to tell you something, and it's that actionable insight, finding out what you should be doing next, when you should be maintaining this, the fact that you should be maintaining something even though it doesn't look like it's broken yet. Those are the insights and the value that the digital twin adds. Look at this. I love this. Imagine a little knob. I can sit and look at that for hours. Okay, so digital twin is IBM's is built on an open industry platform, on Bluemix. We use cognitive computing to not only build, the analytics comes in a spectrum. First of all, you've got simple statistics, then you've got the digital model with a parametric model of the physical system, but then you start to apply machine learning and AI in order to do the hypothesis-based stuff. So you say, of these 100 things, those two appear to be behaving differently. I don't know what's wrong with them, but they're just different. So you go and have a look at them and go, okay, yes, you're right, you spotted something there. There's a particular bearing is running hot or something. So you then tag that feature in the data which says, if you see this, then bearing is running hot. Next time that same feature appears in one of the other ones, you go, the bearing's running hot over there. Dispatch the right person with the right skills, the right parts in their van to go and fix it. So the system appears to have learned and become more intelligent. And then there's dynamic recalibration. You twist the little knob. I wanted to be able to turn it up to 11. That'd be quite cool, wouldn't it? Up to 11. That's the constant iterative process of matching what you're seeing in the real world with what the digital twin's telling you. So when you first build a digital twin, typically it doesn't behave the same way as the physical system does at first. So you have to debug it in the same way as we have to debug any program. And it might be that you've brought in not enough data sources. So I was having a conversation with somebody yesterday, and they're saying how many parameters you have to put into your digital twin. Does it have to be a complete facsimile of the physical system, or can you get away with fewer variables to make it simpler? And I said, well, it actually depends on what outcomes you're looking for. So start on the right-hand side, as my data scientist friends say. Work out what outcomes you're looking for, then work back from that to work out sort of necessary and sufficient set of variables from the sensors that you need to make the observations you want and the synthesized values from those observations in order to drive the equations and the models that you want to build. So we're constantly comparing the reaction of the twin to the physical system. So for example, in my house, there's a kind of digital twin based on the current consumptions of some of the appliances, and that calculates at any given time what the total power consumption of the house should be. If I compare that with my energy monitor and it's different, I can go, we must have missed something out, or maybe there's something that's triggering in the model that's not in the real world, or vice versa, and I can then kind of debug it to find out what's wrong. So that dynamic recalibration could be automatic, could be manual, but you've always got to have the checks and balances in place to make sure that your digital twin's not going off over here while your physical system's going off over there. And that's part of the sort of the development and tuning process. This is our lovely Highlight Towers building in Munich, the Watson IoT Center. And we've kind of made that into a digital twin showcase. A number of dynamic dimensions to that. One is for comfort. So we've got a thermal model of each floor where we think, based on what we know about the heating and cooling system, what the temperatures should be. And then we've got sensors, heat sensors all over the floors, measuring the actual temperature to give us the ground truth as to what the real temperatures are. And then we can then tune the model so it's more reactive. So we can say, okay, if we get a whole bunch of people in a meeting up here and we turn on the aircon down there, we can play the numbers in the model to see what the heat map should look like, and then we can compare that with the heat map should we actually do it, and then we can use that to converge, and we use learning algorithms to automatically converge down to a sensible model, a fairly accurate model of what the heat dynamics are of the building. For efficiency, we've got a model which we use in our employee application, which allows you to do more efficient hot desking. So you can it'll recommend to you seats that should be empty based on which day of the week it is and what time of day it is, based on the historical behavior. And that model is tuned from real-world data, from motion sensors above the tables and little detectors underneath the table, which tells when like somebody's knees are actually under the desk. So we've got real-world data there, plotting over time who tends to be at what desks where, because even in a hot desk environment, people tend to have their favorite seat by the window, don't they? So they're all sitting there. So we can use that to tune the model, so we can recommend with some certainty where there'll be a free space for at least half a day based on the previous history. We've got environmental sensors all over the place. We're using a product from a company called Yancey. Other environment sensors are available, and this allows us to, again, plot the things like CO2 level, temperature, humidity, light level in rooms where we know the meeting's taking place, and we've noticed that CO2 level starts to climb when there's a lot of people in a long, boring meeting, and they all get sleepy. So we've got little orbs on the table that glow red to wake people up, and then we can actually use that to drive things like opening the windows or blasts of cold air or whatever it is to balance out that heating. And again, we're getting ground truth from these sensors, plotting what the model says should happen from the occupancy and the temperature and the booking schedule for the rooms against the actual values that we're seeing in the real world. Now, there's a couple of client case studies. This is Schaeffler, who make trains, and it's the most gratuitous animation ever. This is a train, okay? Going to a little video clip might have been better, but this is an actual animation of a train. And one of the things they're concerned about is the wheel bogies, these bits here, which obviously as they go along the track, the wheels heat up and they get worn, and they're obviously a bit of a risk when it comes to safety, so they need to maintain them very carefully. So we've got a digital twin model of a bogie going along a track, and they've got real-world sensors on the things measuring the temperature of the wheels. And the digital twin model looks at what the temperature should be based on the speed and type of track and curvature and how many hours it's been running and all these different things, how much it's been braking. We can then compare that back against the physical model to tune it, and then they can, oh, we've gone around again, look at that. And then they can, ooh, that's good, isn't it? So one of the things, because this is a system of systems, it's componentized, it allows you to go back into and get full traceability across the entire supply chain, right leading back to the design of these components. So if they discover a systemic problem, they can trace back into it and find out where that happened. By running algorithms against the data and looking back into the historical data, they can optimize the service schedule. Obviously, they don't want to do too little, but they don't do too much either. Just the right amount of maintenance. And also by playing what if, to basically take an ensemble of digital twins and play what ifs on each of them. They can say, what if we did this, what if we did that? They can actually look at they can evaluate the envelope for safety and speed and work out, make sure they're sort of safely inside it in order to optimize their train speed. So that's bringing them a huge amount of insight and great value. Another example is Airbus. I'm sure you know Airbus make planes. I'm sure if Adrian was here, he would tell us what sort of plane. I'm sure Adrian is here. So this is a plane flying in wind and rain. Another gratuitous animation. And so they've built a digital twin of this particular type of plane from the original engineering diagrams. So they've built all the systems of systems inside each other, all into this big asset management system, built a digital twin from it, and that enables us to, when it's in flight, evaluate so it doesn't get the data. It doesn't get the bulk data when it's actually flying. It waits until it lands, and it does a big data offload over Wi-Fi at the boarding gate. But then that feeds into the twin with all the timestamp data, so we can evaluate the actual performance of the fleet of aircraft in flight. They can optimize operations, the maintenance and the loading and the aircraft things they do. Another interesting dimension of this is looking at a whole bunch of planes in a lot of different environmental conditions to find out how they behave in things like rain and lightning and heavy winds. And just measuring one plane doesn't really give you enough. If you feed in a parametric data from all the planes, you start to build up a model of what a plane would do in certain environments. And then you can again play what ifs. What if we tried to land in a 90-mile-an-hour headwind or something? And all of that feeds back insights into the design process, because it's those engineering diagrams from the design process which are actually forming the skeleton of the digital twin around which the data sits. So the benefits it's brought to Airbus is that when they've got multidisciplinary teams working on these things, they're all working from the same set of diagrams. Although it's systems of systems from hundreds and hundreds of different suppliers, they're all in the same model working out what's going on. If they want to play what-if games and understand the impact of changes, rather than having to try it out on a real plane, fly it to see what happens, they can play it out on the model first to go, what if we open this valve half a turn, what would that change, how would that change the airflow or whatever. They can play that out in the digital twin to see what would happen and discuss that. And they've also got consistency between viewpoints, so all the different agencies that work on a plane during its life cycle, they're all talking the same language because they're all in the same model, so at least it's a sort of homogeneous design. The IoT aspect isn't really key to this part of it, it's the fact that it's a design model built on the original engineering diagrams. So digital twin brings you the ability to design better products, achieve faster time to market, and offer new services and business models. One last gratuitous animation, without sound this time, and in our world that's all based on Watson IoT. Thank you. I've got 2 more minutes. So I've got 2 more minutes. I just wanted to show you one more thing. Nothing to do with digital twin. Quite a lot of people yesterday saw me playing with this thing called a glow orb. It's a little shiny LED orb thing. I just wanted to share with you the rather delightful out-of-box experience of if you buy one of these things. I make and sell these. If anybody would like to buy one, come and see me afterwards. Special Thingmonk price. They're normally £20, but you can have them for £15 here. Right, so that was so you unbox it, plug it into some USB power, and it clocks onto your Wi-Fi. I've already connected to the Shoreditch Wi-Fi. If it can't find the Wi-Fi, it goes into access point mode, offers you a captive portal where you can configure the Wi-Fi, and then it reboots and lets you connect. And it connects to your Wi-Fi to the IoT platform, and each one has a little short URL on the bottom of it. I can have my screen back, please. Gracias. And if you go to that URL, here's one I made earlier. Just reload it, check it's the right one. Okay, it's got a bit of JSON. Those of you keen Node-Redders will recognize that as a bit of Node-RED. If we copy and import that into our favorite Node-RED window, doesn't matter where you do it, it comes up with a little flow, which is the controller for that glow orb. So if I deploy that, and then click red, hopefully it goes red. Oh, bollocks. Oh no, normally it just works. We've got the right code, hang on. Check I've got the right. Yeah, that's weird. Okay. Obviously you won't want to buy these because they don't work. I've got demoitis. Okay. That means it's connected to the platform, so now it should. No, it's just not controlling it. That's very weird. Okay, normally that would just make it turn red, green, or blue, and you just send it a color, which is like the web color, like hash FF0000, and the orb goes that color. Charlie and others will attest that it is as simple as that. And yesterday we had one of those micro bits where you tilted it different ways, and it went one of 4 different colors, which is really, really cool. Anyway, if anyone's interested in a glow orb there, it's a single pixel display. Great fun to show the output of some IoT system. Come and see me later, as I mentioned, special Thingmonk price. Thank you.